Well, hello guys, and welcome back to Mr. G Physics, the channel that can help you to improve your marks. I'm Mr. G, and this time we're going to be speaking about free body diagram. But before that, if you didn't subscribe to the channel, don't forget to subscribe so you can get all the notifications and videos I post on regular basis. This time, as I said, we're going to be learning about free body diagram. Previously, we spoke about the force diagram, which is a sketch, but here we have certain or few differences. So what is a free body diagram? In this case, the object of interest is drawn as a dot. So we are not going to have a box here, we're going to have a dot, and all the forces acting on the object will be represented as vectors pointing away from the dot. That is important. So the object will be a dot and the forces will be pointing away from the dot. Now, also very important, sometimes if you are working to solve a problem, it will be convenient to include the axis in that free body diagram. However, be careful. If the question asks you to draw a free body diagram for marks, then you shouldn't include the axis. However, if you draw in the free body diagram because you want to solve the problem, it will be recommended to draw the axis. It's kind of a contradiction here. And let's begin. Let's go to the same scenarios we done in a previous video. And this one was the first scenario we're looking about, an object that is at rest on a horizontal plane. That was the force diagram. Now in this case, how we represent the free body diagram. So there is not going to be an object, we are going to represent a dot, and the forces will be all away from that dot. So the normal force is a vector pointing all the way up. In this case, this one is the normal force, and the weight is pointing all the way down. That one here is the weight of the object, and that's it. This one is the free body diagram for that situation. Okay, let's see the second scenario, also scenario we explained previously. In this scenario, the object is moving under the influence of a pulling force horizontal to the surface. So how do we do the free body diagram? This one is the force diagram. Well, we represent the box as a dot, and all the forces will be pointing away from that dot. So the normal force is pointing straight up. This one is the normal force. The weight is pointing straight down. That is the weight of the object. The force applied, pulling force, is to the right. This one is the applied force, or pulling force. And there is the kinetic frictional force in the opposite direction, to the left in this case. Guys, this is the free body diagram for that situation. It's very simple. Okay, this is the object, is the dot in the center. You will get 1 mark for each force whenever you do a free body diagram, and it's more common in the exams. In this next scenario, we have a force that make an angle with the horizontal, also seen in previous video. This one is the force diagram. Now, for the free body diagram, quite simple. We have the dot, and then from the dot we represent all the forces acting on the object, keeping the direction as they are. So in this case, we have the normal. There is the normal. We have weight. This weight is pointing down. Let's make it a little bit larger. I'm going to explain now just why it's a little bit larger than the normal. We have an applied force that make an angle with the horizontal. That one could be the applied force. And there is a kinetic frictional force pointing in the opposite direction of motion. This one is the kinetic. Let's write kinetic. There we go. And this one is the free body diagram. Okay, now sometimes it's recommended for you to work, not for mark. For mark is this one the one, but for you to work, sometimes it's recommended to do the axis. And if you have the axis, all you have to do is to represent the forces again, exactly as it was before. Now, why would I want the axis? Well, because of the applied forces in between the axis, and when we learn about vectors, we learn that we have to get the components. That is why it's recommended. So this is actually broken into components. So with this axis, you get the idea that here in the X, what you have is this applied force in X. And then you have to take it to the Y and you will get this applied force in Y. That is why the weight is longer, because the weight must be equal to the addition of that normal plus the applied force. This is not exactly accurate, but it gives you the idea. Remember also that this one is 30 degrees in this case, and therefore you can calculate the applied force in X and the applied force in Y. Okay, and if you do calculation, you get that this one is the applied force multiplied by the cosine of 30 degrees, and this one will be equal to the applied force multiplied by the sine of 30 degrees. Now, what is the problem? The actual free body diagram that you're going to be in the exam, what you have to do in the exam, is this one here. However, this one can help you to solve the problem because you already know that they are components. So you must see which one you need to do for the equation you are solving. And then we're going to be looking at one last scenario. In this case, it's an object resting on an inclined plane. So this one could also be tricky. That's why I do recommend to draw the axis as well as the component. Now, if you don't draw the axis, what we have the object will be a dot. Let me just fix this picture a little bit. Okay, so what we have here the object, and then on that object we must keep the directions the same as they are in the force diagram. First we have the weight straight down. This one is the weight. You can see it straight down. Now the normal and the frictional force must form a 90 degree. So the frictional force in this case is slightly in this direction. We keep the direction of the frictional force. That is the frictional force. In this case is the static frictional force, right? And then the normal force must form an angle of 90 degrees to that one. In other words, this one is the normal force, and this one is the free body diagram for that specific situation here. However, I do recommend you to draw it with the axis. So let's do it here now. If you draw the axis, the x-axis will be on the surface. So here are the axes. Now, what forces are acting there? There is weight pointing down in this direction. There is friction pointing up the axis. This one is the static frictional force. And we have the normal up the axis. There we go. This is what we have here. All right, but now we go back to the problem of component. The W, the weight is in none of the axes. So you can determine the component. So you will have here, in this point here, this one is going to be weight in the y-axis. I am working on the y-axis now. Let's just fix that word there. This one is weight in the y-axis, and if you take it here all the way to the x, you get here weight in x-axis. You can see that weight is in none of the axes. Now also something very important to remember, so make sure you take the note. This angle theta we have top there is going to be equivalent to this angle here. This is going to be the theta of inclination, that in actual fact, just for you to get an idea, will be this theta here. That theta is the same. So saying that we can calculate the W in Y and the W in X, and he is slightly different. In this case, weight in Y is equal to weight multiplied by the sine of theta. The theta is the angle of inclination, and then W in X, or weight in X, is equal to weight multiplied by cosine of theta. This one is a little bit different. This theta is the angle of inclination, as you can see, that is theta. And guys, I hope you understand this is all for now about free body diagram. We look at 4 most important scenarios. There can be many. I cannot have all the possible scenarios in this work. This one is quite important and it could be tricky. So if it helped, well, subscribe for the channel, thumb up, and then I'll see you next time. Mr. G here.